In this last segment, I just want to take a few minutes and summarize everything that we have done. And let me emphasize again that if something is not clear or a little shaky, it's really important right now to go back and go through that material, come to office hours, ask me questions, talk to the core staff, because everything we do from now on is going to build on these concepts. So if you're unclear about how we got to the standard linear algebraic framework, matrix multiplication, vectors, all of those things have to be really solid because everything we do from now on is going to build on that. So please take a moment and make sure that you understand everything, and that's why I'm going to summarize it here so you can see all the various pieces. So let me remind you again that the game we are playing is that we want to solve simultaneous linear equations. So I give you a linear equation, x plus y equals 5, 2x minus y equals 1, and we saw three ways of solving it. The algebraic solution, where you isolate one equation in terms of one variable, you substitute that into the other equation, you solve for one unknown, you back substitute it, and you get the other one. And perfectly fine, nothing wrong to do that. You did that through a lot of years of grade school. The problem, of course, is that when we start to get to 3 unknowns, and then 4 unknowns, and 5 unknowns, and 5 constraints, this becomes super tedious and doesn't really generalize very well. And it doesn't really give us a lot of intuition about the question of unique solution, no solution, or multiple solution. You got to sort of just work it out and then see where it all comes out. Now, we saw the geometric pictures that these equations each correspond to lines. If those lines, what we're looking for is the intersection of those lines. And here, we got a little bit of insight into no solutions. The lines are parallel, or infinite solutions. The lines lie on top of each other. But again, this got a little messy once we got into higher dimensions, because in 3 dimensions, I have to intersect 2 planes to get a line, and then intersect that plane with another plane with that line to get the point. And then in 4 dimensions, I'm dealing with hyperplanes, and so things don't really generalize that well, or that easily, or that intuitively to higher dimensions. And then, of course, we got to the linear algebraic picture. So we rewrote our equations as finding 2 scale factors, such that when we multiply these vectors, the columns in the linear equation, they sum up to the right-hand side. And of course, we rewrote this equation. We took these 2 vectors and we simply bundled them into a single matrix. So we have a matrix times a vector is equal to a vector. Again, remember that I will denote matrices as capital letters, vectors as lowercase letters with a little vector on top sign, just to remind myself that we're dealing with vectors, not scalar values. And then, of course, we introduced the concept of a matrix inverse. Inverse the matrix here, I get the identity. The identity times anything is itself. And so I've isolated the unknown. And here I have a simple calculation. This is now just a 2 by 2 matrix times a 2 by 1 vector. I get a 2 by 1 vector. That's my unknown, home. And I haven't gone through it all, but I will tell you it's relatively straightforward to calculate the inverse of any square matrix that you want, 3 by 3, 4 by 4, 5 by 5. So everything we are doing here is equal number of constraints and unknowns, so we will only deal with square matrices. In the next set of lectures, we'll deal with when we have more constraints than we do unknown, but for now, let's not worry about that. And what's nice about this solution is, first of all, that it generalizes very easy because the matrix inverse generalizes very easily. And we got some real intuition for the problem by simply looking at that matrix inverse, and in particular the determinant of this matrix. When it was 0, we saw exactly the types of problems that we expect to see for degenerate solutions, where you have an infinite number of solutions or no solutions at all. So here are the core concepts you should have. Solving linear equations, the algebraic, the geometric, and the vector picture. You should be able to understand and make sure you're comfortable with all the algebra and the geometry in the linear algebra. And for the linear algebraic solutions, I, of course, expect you to understand what vectors and matrices are, how to do matrix multiplication, and matrix inverse, at least for the 2 by 2 matrix. Okay, so that's in some ways the sort of linear algebra 101. We went through some really basic concepts in linear algebra. If this was a full-blown linear algebra class, this would be like the first week of class and we would carry on. But this is not a linear algebra class, but I want you to know these tools because they're incredibly powerful. And using this as scaffolding, we are now going to start talking about how you apply these tools, not just to solve abstract linear equations that I threw up on the slide, but to solve real-world and interesting problems and extract meaning from our data. And so with that, we'll pick it up with a few examples, and then we'll carry on from there in the last 3 lectures of this class. All right, we'll see you in a few minutes.